So last time we were faced with the question, how do we solve the log base 3 of x minus 4 plus log base 3 of x plus 4 equal to 2? And if you solve that correctly, you should have gotten just a single answer, x is equal to 5. So hopefully that was not too much trouble, but if you did not get that, go ahead and check. I'd specifically recommend that last example in video 3 in terms of helping you get through that one. Okay, so in this last video, we're going to turn our attention now to inequalities that involve logarithmic functions. Now, what we're going to find is that this is sort of a marriage of a lot of the skills that we've already picked up with solving general inequalities, like finding critical values and setting up sign diagrams, along with the skills we've picked up in solving logarithmic equations. So in general, if we had to sort of lay out a process for solving logarithmic inequalities, this would probably be it. This will get us there most of the time. So the first thing we should do is identify the domain, that meaning the restrictions that we place on x. This is going to kind of give us a window to look into for our solution set and chop out some of the fat that we don't need to worry about. Once we can do that, then we're going to go ahead and find our zeros or our critical values. These are going to be the skills that we just learned in the first 3 videos implemented here. And then lastly, we'd set up a sign diagram and then evaluate the inequality. And that's going to be a lot of the skills that we've picked up over the course of the semester with solving inequalities. So that's going to be the basic setup. So let's try a couple of examples and see how those work. So let's start with the ln of x minus 3 is strictly greater than 0. And let's just try and stick with those 3 steps and see how that works for us. So step 1, we need to identify the domain or the restrictions that we have on x. Well, this is where we can get started, is that this term right here, the x minus 3, that's our argument that always has to be positive. So we can start by saying that needs to be greater than 0, because we can't take the log of 0 or a negative number. And because of this, we get our restriction on x, which is x has to be strictly greater than positive 3. So we can now focus our attention on just those numbers. And then for step 2, we're going to go ahead and find the zeros. And in order to do that, we're going to go ahead and take our inequality and we're going to set it equal to 0. So we're going to solve this by setting it equal to 0. Now this is nice. This is pretty nicely set up for us in that we've got our isolated log on the left and we've got our only constant on the right, which is in this case 0. So if we were to convert this into an exponential equation, this would end up being x minus 3 is equal to our base, which is e raised to the power of 0. Or in other words, we'd have x minus 3 is equal to 1, or x is equal to positive 4. So there's our 0. Luckily this, well, doesn't matter, luckily or not, but it so happens that our 0 does fall within our domain from x being greater than 3, so it's actually going to sort of come into play in solving this. And that's the only 0 that we're gonna have. So let's go ahead and go to step 3. So we're going to set up our sign diagram and evaluate. So we'll go ahead and we'll draw out our line. Now this is a good place to start implementing these restrictions. So we're only going to go from 3 to positive infinity. And we're never going to include 3 because it's strictly greater, so I'm just going to go ahead and I'm going to put an open dot there, just so we know not to include that. And then we can go ahead and mark down our 0, which is positive 4, and we can mark that as this is a 0 of our function. So as we've done before with these inequalities, is we're going to go ahead now and we're going to go ahead and we're going to test points. So I'm going to look at my intervals here And from this interval, I'm going to pick 3.5. And in this interval, I'm just going to pick a big number like 100. And those are going to be our test points. So if we were to test these to determine, we're trying to find out whether this function ln of x plus 3 is positive on or negative on these intervals. So if we tested x is equal to 3.5, we'd have the ln of 3.5 minus 3, and this would just be the ln of 0.5. And what we notice here is that this is going to be a negative number. We could get that on our calculator, or we might just know that the log of a number less than 1 is going to be negative. So that's going to be our negative number, and we do the same thing with 100. If we plugged 100 in, we'd have the ln of 100 minus 3, which would be the ln of 97, which is going to be a nice, juicy, positive number. And we can go ahead and we can throw that information now on our sign diagram. So on this interval, our function is going to be negative, and on this interval, our function is going to be positive. So we were originally asked to evaluate when is the ln of x minus 3 strictly greater than 0. Well, it's going to be strictly greater than 0 on this positive interval. Now, we're not going to include 4 because that's where it's equal to 0, but we are going to include all of the numbers on this interval greater than 4. So if we were to put our solution in interval notation, we'd say that, so our solution is going to be from 4 non-inclusive to positive infinity, and that would be our answer. So we could pick any number on this interval, plug it back into our original inequality, and we'd have something strictly greater than 0. So that's our first one, so not too bad. And we're going to use this exact same method and approach on this next one here. A little bit more complicated, but not too bad. So we've got x times the log of x minus x is less than or equal to 0. So let's go ahead and see what we can do with this one. Let's stick with our standard approach that we outlined at the beginning of the video. So we're going to look at our restrictions. Well, we've got one log function here, and the only restriction we're going to have on our domain is that argument, namely x, has to be strictly positive. So this is a pretty easy one. We just got x has to be greater than 0. Okay, so that's that. So now let's move on to the sometimes most challenging part of this, which is finding the zeros. It just kind of depends. So what we're going to do is we're going to take our function that's been isolated and set it equal to 0 and solve for it. So we've got x times the log of x minus x is equal to 0, and we're going to solve this. Now, this is a little bit different from other ones that we've done in that we've got x's floating around that are not inside logarithms. But we can handle this. This is okay. One thing we might notice is that we could factor an x out of these two terms on the left. So let's go ahead and do that first. I'm going to pull an x out, and that's going to leave me with log of x minus 1 is equal to 0. And now these two factors are equal to, or the product of these factors is equal to 0. So we can now set up these two scenarios. 1, x is equal to 0, and then 2, the log of x minus 1 is equal to 0. And we can go ahead and work through this one. This is a regular logarithmic equation, so we add the 1, and we've got an isolated log on one side, we've got a constant on the other side, and we're just going to rewrite this as x is equal to 10, which is our base, to the power of 1, or essentially just equal to 10. So these are our two possible solutions. Now notice we get to chuck one of them right off the bat, because if we look at this x equals 0, well, we're told that x has to be strictly greater than 0, so we get to throw this one away, and we've only got the 1, x is equal to 10, that we have to use in our third step. So again, that is directly due to that restriction. So now we're going to go ahead and we're going to set up our sign diagram, and we'll draw our line as we go off to infinity, because we're looking just at x values greater than 0. I'm going to put an open circle there because we can't use it. I'm going to drop my only 0 on my number line, which is 10, and now we just go about picking points and testing them just like we did before. I'm going to pick 1 from this first interval and good old 100 from this second interval. And if we test these, so we're going to take x equals 1, and sometimes one of the questions is, well, what do I plug these into? And what we're going to be plugging them into is this part right here, back in step 2 where we had the actual equation. So we're going to plug those in to the zeroed out part of our equation. So we plug in 1, and that's going to give us 1 times the log of 1 minus 1, and the log of 1 is just going to be 0, so we're going to have 1 times 0 minus 1, so we're just going to have a negative 1 here. So this test point gives us a negative value, and if we picked the other one, 100, and plugged it in, we'd have 100 times the log of 100 minus 100. Now the log of 100 is 2, so we'd have 200 minus 100, which is going to give us 100, which is going to give us a positive value, because that's really all we're interested in, is whether it's positive or negative. So we're going to record this information on our sign chart. So this interval is negative, this interval is positive, and what we originally wanted was, when is this function less than or equal to 0? It is equal to 0 here at 10, and it is less than 0 on this interval, and we will circle but not include that 0 point right there. So that's our solution interval here. So our solution is going to be from 0 non-inclusive to 10 inclusive, and if we picked any number on that interval, that would satisfy our original inequality. So that's our solution. Okay, so that's all we've got for section 6.4. We'll be using these skills again when we get into applications, and that is all for this series of videos. Thanks.